Okay, so I'm going to talk a little bit about building exponential functions with e instead of using our more familiar where you just see what the growth rate is. And the two models I want to compare are, let's say we have one model where you start with 10, maybe this is population. So let's say you start with 10,000 ants and they grow at 2% or 5% uh, every year. So 5% raised to the x. Okay, and let's give ourselves a different viewing window here. And let's make our x go to 50. And let's make our y go to 100. All right, so that's a pretty common, exponential graph here. Maybe the 5% is every month. So number of ants starts at 10,000. Every month you've got 5% more. This is very familiar. Well, it turns out you can model the same situation like this, 10e to the 0.05x. What I want you to notice is that the red curve and the black curve are pretty similar. The red curve is a little bit bigger than the black curve, but they both basically represent a 5% growth. I want you to notice when you look at the way these are structured, we use 1.05 for the black curve because that's 5% added to 1 each, what did I say, month. So at the end of each month, you have 5% more than you did at the beginning of the month. This second one is a little bit weirder. I'm going to grab the e and the 0.05. I want you to think, what did e to the 0 equal? Well, e to the 0 is the same as 2 raised to the 0. It's the same as 10 raised to the 0. It's the same as pi raised to the 0. Any base to the 0 power is equal to 1. So when you're raising it to the 0.05, you're saying 5% more than e to the 0. So it's a similar idea that you're always bigger than 1 in order to increase. When it's 1.05, you're 5% bigger than multiplying by 1. When it's e to the 0.05, you're 5% bigger than e to the 0. So that's a nice connection because in both cases you're multiplying by a number that's bigger than 1. Just to show you that in a slightly different way, if I wrote 10 times 1 raised to the x, it's a flat line. And if I said 10 times e raised to the 0x, it's a flat line. And so in both cases, I just increase what I'm multiplying by or increase that power a little bit more to give that percent growth. Okay. Now, what's the difference? You should be wondering, why would we have two different ways of representing a 5% growth? And it's because if you watch my first video about E, remember the idea is that E is approximately 1 plus 1 over x to the x for big x values. So what that means is if you're doing something and adding a really small amount a really big number of times, then E is a good approximation. So E is good when the growth doesn't happen periodically, but when it happens continuously. So what I mean is, are you growing by a percent by adding it all at once at the end of the time period? Or are you adding little bits all throughout the time period? With ants, I'm not an ant expert, but I don't think they wait a full month to have more ants. There's sort of reproduction happening all the time. And over that course of the time, the number is continuously growing. So the 5% growth is always at every moment applying to a slightly bigger amount. And that's why the red curve is bigger than the black curve. The black curve waits until a month to have a full 5%. The red curve gets 5% at every instant of what is there. So the E thing is this idea of it's continuously growing, whereas the 1.05 is the idea that it periodically, that at the end of every time chunk, it grows by 5%. Kind of like a geometric sequence is disconnected. It's a similar idea to that. Okay, so that's the main idea. I want to show you something about E. These are approximations of 5% growth. If I change it to 3% growth, you'll notice that a little bit flatter, of course. You might also notice that they are closer together. And if I change it to 1% growth, they're even closer together to the point where you can't really tell any difference between them anymore. So the E actually works best as an approximation when the R value is small. When the R value is big, like say 10% growth, then there's a more clear divergence between the two of them. So E has two sort of different purposes for modeling. It models that continuous growth, where at every second you are growing in relation to how much you have. So that's good for something like if bacteria are growing, or if you have radioactive decay, or something where it's always cells dividing, where you always have it related to how much is there. And E is a really good approximation when you have that periodic growth where it's disconnected chunks. And it's a better approximation when you have a small rate of change, a small R value. So to kind of summarize, you're going to use it to write equations where you have an initial amount and you have a percent change and a time right there. This is the beginning amount, like in my example 10,000. This is the initial amount. And the R value is the percent change. Just make sure to express it as a decimal. So that's about it about using E to model. And that's one reason why you might like the number E itself. E has a lot more applications if you go on to do calculus. It also surprisingly has a lot of applications with complex numbers. So there's a lot more to E, but this is just sort of scratching the surface. So let me know what was confusing, and I will help out.